Okay, as we come to a new calculus topic, there's four topics at the end. They're not really connected together, but they're saved for the end of the curriculum for one main reason, is that they involve both integrals and derivatives, and they're also kind of segregated pieces of the puzzle that are tools that help you solve other problems. And we're going to talk today about a special rule, and the name of the rule is, there's a thing right there. It's called L'Hopital's rule. That's pronounced L'Hopital, like L'Hopital is what it's pronounced. And L'Hopital was a French mathematician, and he discovered a relationship between functions and their derivatives to find their limits. I know it's been a long time since we've done limits. And limits are actually very easy to find for most functions. The limit is the value you approach from the left, and the value you approach from the right end up being the same number. And limits are usually very straightforward. The limit is x approaches 3 of x squared. If you put the number in and get an answer back, you'll know what the limit is. I'll put 3 in for x. I get 3 squared, and the limit of that function is 9. And that makes sense. It's a continuous function. As x approaches 3, in the y direction, from both sides, y approaches 9. So limits are very straightforward unless we have something known as indeterminate form. And let me give you an example of a function that would be like that. Indeterminate forms, there's many different versions of indeterminate form. The most common being 0 over 0, infinity over infinity, 1 to the infinity, 0 to the 0, infinity minus infinity, and etc. Versions like that. The ones we're going to see, oh, I left a couple out. I also forgot about infinity over 0 and 0 over infinity, but I think you can see the relationship here. All of these are things where we don't know what are going on. We're going to be very careful. We do know what's going on when we have 0 over 1. With limits, that is actually equal to 0. And I'm going to be very careful about this when we use limits. If we're looking at limits of 1 over 0, not values, but if we look at limits of 1 over 0, then those numbers are heading off towards infinity. But I'm going to be careful about that. So let's talk about a problem in indeterminate form. Let me get a new page right here. Oh, my first question of the day, question number 1, is what time is it right now? What time are you watching this video? I'll even write down what time. So we have that information right there. So we're going to look at an example of a problem using L'Hopital's rule. Just getting a good one right now, so I have it. And we're going to start with y equals. Oh, I'll take that back. We're going to find the limit as x approaches 0 of x squared plus 2x over x. What would the limit of that function be? Well, let's go ahead and fill the 0 on in. If we fill the 0 on in, I get that's equal to 0 plus 0 over 0, which is 0 over 0, which is indeterminate form. Now, when we had problems like this in the past, what we started doing was using synthetic substitution. We'd factor things out. We'd take pieces away. I'm telling you, you don't have to do that anymore. And that's a good thing, because this L'Hopital's rule is going to make your life easier. You just have to remember that L'Hopital's rule only applies to limits, not to values. And L'Hopital's rule, which I'm going to write out once here for you, says that the limit as x approaches c of f of x over g of x is equal to the limit as x approaches c of f prime of x over g prime of x if f of c over g of c is indeterminate. What? So many words, Mr. Brigham. What are you talking about here? I'm going to break it down for you. If you have a function, and it's made up of a quotient, as all indeterminate ones are going to be, and you put in the value c into the top and bottom, and you get indeterminate form, the limit of that one is the same as the limit of the derivative of the top over the limit of the derivative of the bottom. So all you have to do is take the derivatives to see what happens. And I can prove that's the case with the following problem above. Limit as x approaches 0 of x squared plus 2x over x. So instead of putting in 0, I'm going to put in 0, I get indeterminate form, 0 plus 0 over 0. I'm going to keep the word limit. I've got to keep that going. Limit as x approaches 0. I'll take the derivative of the top now. The derivative of the top is going to be 2x plus 2 over x. Oh, sorry, over 1. 2x plus 2, that over 1. And now I can put the 0 on in there, and I get the limit is equal to 0 plus 2 over 1, which is equal to 2. Ooh, that was nice and easy. Did it really work? Let's take a look at that problem again. I'm going to write down the limit. It's x squared plus 2x over x. So the first thing I'm going to do is I'm going to factor out, and before I work the problem out, I don't have to do this. This is just a proof of it happening. I'm going to factor out an x. It's the limit of x parentheses x plus 2 over x. I factored out an x. And I could cancel these two things out, much like I did with the synthetic substitution before, and now fill in the 0, and I get 2. And hey, I got the exact same answer. That's awesome. This type of problem works for any fraction where that happens. And actually, you can apply it over and over and over again. You can apply it multiple times if you have to. Let me give you an example where that would be the case. So let's look at this next function. I've got the limit as x approaches infinity of x cubed plus 2x squared plus 7 over x over 2x to the third plus 5x squared plus 7x plus 2. Long problem. I actually already know what the answer is just by looking at it, because I know certain things are insignificant, but we'll talk about that together in class. As a matter of fact, question 2 is, how did Mr. Brigham say he knew the answer to the problem? It starts with in, and the rest of it rhymes with ignificant. But let's go ahead and put in infinity into that equation, and I already know, if I put infinity in the top, I'm getting infinity on the top. If I put infinity in the bottom, you can't put infinity in there, boss, it's not a quantity. Correct, but I'm not working with quantities, I'm working with limits, which means I can put that number on in there. And I get infinity over infinity, which is not equal to 1. It's indeterminate. There's all different types of infinities. Indeterminate. So what I'm going to do is I'm going to take the derivative of the top and the derivative of the bottom. You can only do this when finding limits. And you've got to carry the word limit with you when you work. So it's 3x squared plus 2x over 6x squared plus 5x plus 7. We'll go ahead and put infinity in again. Oh no, we get infinity over infinity one more time, which is still indeterminate. Okay, let's keep going. Let's try it again. You can use this rule as many times as you need to. Limit as x approaches infinity. Let's take the derivative of the top, which is 6x plus 2. And the bottom is 12x plus 5. Put in infinity again. Oh, still indeterminate. I'm not giving up, boss. I'm not giving up. X approaches infinity. I'm going to take the derivative of the top, which is 6. Derivative of the bottom, which is 12. And there's not even a place to put infinity in there. I'm just going to solve that one out, and the answer is going to be 6/12 or 1/2. Now the reason I was able to quickly identify what was going on, when I'm heading for 0 and I'm heading for infinity, the only exponents that matter are the biggest exponents. I'm heading for infinity. Everything else becomes insignificant, becomes so small, becomes trivial. But I know with this equation, for the most part, I could have just eliminated these extra things right here and just worked with that fraction, and then this would have canceled with that, and I would have been left with 1/2. Oh, pretty Pretty sneaky move. Let's just try one more so we can see how we're going here. We'll try a little more advanced one.
Do you have any deliveries of large things? I'm looking for cardboard.
Nothing.
Okay.
Sorry.
Thank you.
So question number 3 is, what did Mr. Reardon just ask me for as he entered the door? I'll leave that as a question mark for your third question to answer. No, that was my mistake. I shouldn't have put it there because now you're not going to watch the rest of the video. But I'm only do one more problem, then I'm going to stop. Let's go to limit as x. It works on all types of problems as x approaches infinity of e to the x over x squared. Let's put infinity in there. E to the infinite power is going to be infinite. And infinity squared is going to be infinity. So once again, I'm indeterminate. Let's go ahead and put another number in there. Sorry, take the derivative now. Derivative of e to the x is e to the x. Derivative of x squared is 2x. Put in infinity. Arc. Infinity over infinity again. Last time around. Oh, I told you it was the last time, didn't I? Oh, well. Derivative of the top is e to the x. Derivative of the bottom is 2. So now if I put in infinity, I get infinity over 2. This is not indeterminate form. I now no longer have infinity and on the top and bottom or combinations of 0. This one has an answer, and the limit of this function means the top is always going to get bigger and bigger. The limit is going to be infinity. 4 key limits that you should always know that come into play. The limit as x approaches infinity of x, oh, it's not writing very well, equals infinity. The limit as x approaches infinity of 1 over x equals 0. And the limit as x approaches 0 of x is 0. And the limit as x approaches 0 of 1 over x is 1 over 0, which is not a number, but the limit is infinite. These two functions come up a lot. We're going to do basic level problems tomorrow. There's some other ones that don't look like fractions initially, but once you turn them into fractions, you can find the limits for all the problems. I'll see you guys tomorrow.